Welcome to video on CMOS operational amplifiers. So in this video we shall see the design of two-stage opamp. So this is the first part of videos on the design of two-stage opamp. So this is the circuit what we are supposed to design. So it consists of 7 MOSFETs, so constituting one differential amplifier and a CS amplifier. So we have a capacitor CC which is for providing compensation. So this CL is the load capacitor and it is supplied using two power supplies. One is VDD, other is VSS. So this is the expected frequency response. So since the circuit is a compensated one, so we're going to get the frequency response which is shown in the solid lines. So having its cutoff frequency at omega P1 and omega P2 here. This is the phase equation of this particular circuit, so which has got two poles with time constant tau P1 and tau P2, and we have a 0 which is there on the right hand side of the S plane. So that's why it is so this negative sign indicates this is because of pole, and we have a plus term here, so this is positive here. This indicates that the poles are there to the left of the S plane, and we have this plus indicating is the 0 and this minus indicating the 0 is located on the right hand side of the S plane. Now phase margin is we can write this phase equation equal to phase margin by substituting this S by omega GC, and this tau P by its corresponding frequency, that is tau P1 is now represented as 1 over omega P1 and tau P2 is represented as 1 over omega P2, and tau Z is represented by 1 over omega Z. So you can see now we are retaining the negative sign here. So this is the two poles and this is a 0. And we continue with this, and we replace this negative omega GC by omega Z by 180 minus of tan inverse of omega GC by omega Z. And we know that to find the phase margin, S is replaced by omega GC, which happens to be the gain bandwidth. So in these two equations are exactly same, where we are replacing this omega GC by the gain bandwidth, and this is what is the same as the previous equation. And in this equation of phase margin, so let us substitute GB, that is gain bandwidth, as omega GC is equal to, we know the expression for omega GC as GM1 by CC, and the expression for omega P1 is nothing but 1 over R1 GM2 R2 into CC. So this is R1 multiplied by GM into R2 times CC, and we are writing the ratio of GB by omega P1. So we are substituting the values of GB and omega P1 over here, and it is found that this ratio of GB by omega P1 happens to be GM1 R1 into GM2 R2, which we can write it as the voltage gain of the two-stage amplifier at DC. So this is known as DC gain, and we are assuming that the 0 is located far away from the gain bandwidth. So if GB happens to be 10 times of if omega Z, the location of 0 happens to be 10 times compared to the omega GC, that is gain bandwidth. So the ratio of this GB by omega Z happens to be GB by 10 times GB, which is now 0.1. So this equation, so what we have here, so which is in terms of GB by omega P1 and GB by omega P2 and GB by omega Z, reduces to phase margin is given by minus tan inverse of AV at 0 minus tan inverse of GB by omega P2 plus 180 into tan inverse of 0.1, because this ratio is now 0.1. So that reduces to, we know that this AV is far greater than 1. So this tan inverse of a very large value happens to be 90 degree, and for a phase margin of 60 degrees. So this is phase margin, and this is now represented by minus 90 degree, and this tan inverse of 0.1 happens to be 5.71. So upon solving this, we end up with omega P2 can be now represented as 2.2 times the gain bandwidth. Now we are trying to locate the location of the second pole, that output pole, which is at 2.2 times the GB. That is, for a phase margin greater than equal to 60 degrees, the omega z, the zero of the transfer function should be located at least 10 times greater than GB, whereas the second pole, that is omega p2, should be located greater than or equal to 2.2 times GB. So we know that omega z is given by gm2 by cc, so that should be greater than 10 times of GB, where GB is now represented by gm1 by cc. So by those two, by equating these two equations, we'll get gm2 should be greater than or equal to 10 times gm1. So this gm2 is nothing but gm6, this gm1 is nothing but gm1, this is gm1 of the first stage, so this is gm of the first transistor. So gm6 should be at least greater than or equal to 10 times gm1. So this will make sure that the 0 is located 10 times greater than the GB value. Similarly, omega p2 is given by gm2 by c2, which should be 2.2 times GB, where GB is again written as gm1 by cc. So substituting these, we get gm2 is now nothing but gm6. So this is for the second stage. The second stage is represented by the sixth MOSFET, and this CL, which happens to be the load capacitance, is replaced by CL, and this GM of 1 is replaced by GM of the first transistor, and this CC is CC. So we know that GM6 can be written as 10 times GM1, and this is 2.2 times GM1. So by solving this, we get the relationship between CC, that is compensation capacitor, should be greater than or equal to 0.2 times 0.22 times CL. So this should be, the compensation capacitance should be 2.2 by 10 times 2.2 divided by 10 into CL. Now this is one of the important equations which will be used in obtaining the design of a two-stage CMOS amplifier. So we know that ID is given by mu n C ox W by L into VGS minus VTH. So we are writing the transconductance equation in three different forms. So one is under root of 2 ID mu n C ox into W by L, other is in terms of ID and V overdrive voltage, and other is in terms of W by L and overdrive voltages. So these three equations will be using repeatedly in the design steps. And we know that the output impedance of a MOSFET, looking from a drain with the source AC grounded, is given by 1 over ID into lambda. So where ID is the DC current flowing through the MOSFET, lambda is the channel length modulation factor. And ID can also be represented by the same expression. Here I am writing VGS minus VTH as overdrive voltage square, and we write this mu n C ox into W by L as beta, which is a transconductance parameter. So which is now mu n C ox into W by L. So instead of writing mu n C ox W by L, we are writing it as beta. So it is beta by 2. So we can write ultimately the overdrive voltage, which is nothing but VDS sat, can be written as under root of 2 ID by beta. So we are writing this in this form of ID and beta because this is to exactly match the textbook expressions, where it is given as under root of 2 ID by beta as the value of VDS. So this is there in Allen Holberg textbook. So in order to find the IC max, so as we know that IC max is the input common mode maximum voltage. So this refers to as we are keep on increasing the input voltage, one of the MOSFET will go out of the saturation. So it is the verge of the input voltage at which this M1 just goes out of saturation. So we are writing the expression for VIC max considering this VDD, VSG3 and VDS1 and VGS1. So that's what we are writing here. So it is VDD minus VSG3 minus VDS1 and VGS1. So this VDS1 can be written as VGS1 minus VTH because this is in saturation. When it is in saturation, when the MOSFET M1 is saturation, it is VGS1 minus VTH. So upon simplifying, this VGS1 and this VGS will go up. So we end up with VDD minus VGS3 plus VTH1 as the VIC max, that is the input common mode range, which is the maximum voltage. But VSG3 can be further written as, so we know that the current flowing through transistor 3 can be written as half of the tail current, that is ID5, which is nothing but mu1 Cox by 2 into W by L VSG 3 minus VTH whole square. So this we are writing, we are rewriting this VSG3 as equal to under root of I5 by beta 3 plus V threshold voltage of the third transistor. So ultimately we write the expression for VCM Max, that is the common mode range maximum voltage is VDD minus root of I5 by B3 minus VTH3 plus VTH1. So similarly, we can write the minimum common mode voltage that can be applied to keep the MOSFET in saturation region by considering this VSS, VDS5 and VGS1. So that's what we are having. That is VSS plus VDS5 saturation plus the VGS1. So we know that ID1 can be written as I5 by 2. The ID1 is the current flowing through MOSFET M1, which is half of the current flowing through I5. So that's what is given here. So we are writing this VGS1 in the form of I5 and beta. So that's what we are writing here. So VGS1 can be written as under root of I5 by beta 1 plus V threshold 1. So ultimately we write the common mode range minimum voltage should be, that is VCMR minimum is VCC plus of under root of I5 by beta 1 plus V threshold 1 plus VDS at of fifth MOSFET. And there are some other important equations. Slew rate is given by I5 by Cc. It is the rate at which the output changes. And we know that the first MOSFET gain is given by Gm into R1, where R1 is R01 parallel with R02. So it can be expressed in terms of transconductance between the drain and the source as, so R1 can be written as 1 over GDS2 plus GDS4. So which is how it can be written as this R1, the input resistance of the output resistance of the first stage is given by R01 parallel with, R02 in parallel with R04, which can be written in this way. 1 over R02 is nothing but GDS2 and 1 over R04 is nothing but GDS4. So this is how we are writing. And we can also express 1 over R0 as in terms of the current flowing through the MOSFET and its channel length modulation factor. So we can write this 1 over R02 as I5 by 2 into lambda 2, and similarly R04 can be written as I5 by 2 into lambda 4. So which can be rewritten in the form of 2 divided by I5 into lambda 2 plus lambda 4. So ultimately we can write the expression for I1, the expression for the first gain of the first stage of the CMOS amplifier, that is A1, as 2 times GM1 divided by I5 into lambda 2 plus lambda 4. So this is the ultimate expression what we'll be getting for the first stage. Similarly, for the second stage, we can write it as GM6 divided by I6 into lambda 6 plus lambda 7. Again, the current that is flowing through the second stage is I6, so that part is I6, and there is no 2 term here, because in the previous case there was a term 2, which is due to the current flowing through the first stage is half of I5, so that's why that 2 goes to the numerator. But here in this case there is no 2 here. It is GM6 and the current flowing through the second stage, which is I6, and the channel length modulation factor of the second M6 and M7 transistors. These are the equations of gain bandwidth, output pole and the zero frequencies. And we are supposed to now design a two-stage amplifier, meaning that in case of design of two-stage amplifier, we are supposed to estimate the dimensions of all the MOSFETs along with the value of capacitance Cc.